Training diffusion models with reinforcement learning is brutally expensive. When you apply group relative policy optimization, or GRPO, to image generation, you have to backpropagate through every single denoising time step. For a standard 20-step trajectory, that means 20 full transformer backward passes per training group. It's a hard computational bottleneck. But diffusion transformers have a structural property. The velocity predictions and hidden states change smoothly and nearly linearly along the denoising trajectory. What if we could exploit that linearity to shortcut the backward pass itself? That's exactly what JAGG, Jacobian-Aggregated Group Gradient, does. Instead of running W backward passes, JAGG reduces it to just 2. Here's the technical core. The Jacobian of the denoising velocity with respect to the model parameters is approximately linear in the input space during the high-noise regime. JAGG computes cheap upstream gradients for every step, then uses a time-step-weighted linear interpolation of the endpoint Jacobians to aggregate them into 2 composite gradient signals. Mathematically, if the velocity field is strictly linear in the latent and time-step coordinates, this interpolation is exact. The paper proves this formally. In practice, linearity degrades as the image becomes clearer, so JAGG uses a routing parameter called JAGG-frac. It applies the 2-pass approximation only to the early, high-noise groups where the assumption holds, and falls back to exact per-step backpropagation for the later, semantic-heavy steps. The result? A consistent 2x reduction in backward passes, translating to a 17 to 18% wall clock speedup across models like Flux and QwenImage. And critically, generation quality barely moves. The ablation studies confirm that discarding intermediate gradients entirely destroys performance, but Jacobian aggregation preserves the full signal at a fraction of the cost. JAGG turns a fundamental computational bottleneck in diffusion RL into a solved problem. It's a clean, mathematically grounded acceleration that makes large-scale preference alignment for visual generation actually practical. If you're working on diffusion fine-tuning or RL alignment, this is the kind of optimization that changes what's feasible. Let me know in the comments how you're handling backward pass bottlenecks in your own pipelines.